Hi everyone, this is Dr. T. Shivling Swami from PG Department of Physics, Government College, Mandya. So in this lecture, I'll be just giving some introduction to the formalism of quantum mechanics. Till 1900, we used to explain all the interactions by using classical laws, just like Newton's laws of motion, Newton's law of gravitation, Maxwell's equations of electrodynamics, etc. So they were very successful in explaining all the laws, all the mechanics that we find in classical world. But however, around 1900, we faced certain problems in physics, such as problem of blackbody radiation, specific heat capacity of solids at low temperature, etc., which could not be explained by using classical laws. So we needed a new mechanics to explain such properties, and that new mechanics is called as quantum mechanics. So this was developed by the hard work of many great scientists like Max Planck, Schrödinger, Fermi, Dirac, etc. So in this lecture, we highlight the need of new mechanics and the general formalism of so-called quantum mechanics. So we'll start with the basic drawbacks in classical mechanics. So we'll take up stability of the atoms. As you all know that atoms consist of the central part, so which is positively charged in nature, so that is called as nucleus, around which electrons will be revolving. So according to classical electrodynamics itself, if you have an electron revolving around the nucleus, that electron will be like an accelerated charge. So it should emit radiation. So when that electron emits radiation, it should take a spiral path and finally should fall into the nucleus. Therefore, this is against to the stability of the atoms. So atoms should not exist. But we know that atoms are stable. So this was a challenge so that people faced. So this needed a new explanation. The other problem that we found around 1900 is the problem associated with the blackbody radiation. You know that blackbody is one which absorbs all the radiations irrespective of the wavelength. According to Kirchhoff law of radiation, a blackbody should be a good emitter also. In fact, Kirchhoff law of radiation says a good absorber must be a good emitter also. We know that blackbody is a good absorber of radiation, so it should be a good emitter of radiation also. And the radiation emitted by a blackbody is known as blackbody radiation. Suppose if you plot this radiation spectrum, so that means if you plot a radiation as a function of wavelength, so we get a graph like this. So this is the graph that we find. So this is the experimentally observed graph for a given temperature. So this is drawn at 5000 Kelvin. So it consists of all radiations. So many people try to explain this blackbody radiation spectrum by using the classical laws. So we have some important laws like Wien's displacement law. So you can notice that this blackbody distribution is not uniform. So we are getting a curve. So that means each spectrum has a peak. So that means the blackbody distribution or blackbody radiation is not really uniform. So Wien studied this peak, as the temperature increases, say for example from 5000, if we go to some other higher temperature, say 6000, this peak corresponding to maximum intensity shifts towards the shorter wavelength part. Or in other words, this lambda corresponding to this peak, so that is inversely proportional to temperature. In fact, that is related through this equation. This is called as Wien's displacement law. So this lambda into T is constant. So that is equal to 2.9 into 10 power minus 3 meter Kelvin. So this is actually Wien's displacement law. In fact, this is very important law which is used to find out the surface temperature of the stars. So say for example, our sun, surface temperature of sun is about 6000 Kelvin. Once if you know, say for example, take you want to find out the surface temperature of a particular star, say for example, how do you estimate the surface temperature, or how do you know that the surface temperature of the sun is 6000 Kelvin? Only it is very simple. So you take the solar spectrum. So solar spectrum will have a peak. If you know that lambda corresponding to that peak, so then you can substitute here, then you can find out T, because lambda into T is always constant. So that constant is equal to 2.9 into 10 power minus 3 meter Kelvin. So this is how you know the surface temperature of stars are defined or estimated. So based on the surface temperature of the stars, we classify the stars into several groups. You know that O, B, A, F, G, K, M. So Sun is a G star. But same Wien studied this blackbody radiation spectrum, and he tried to give an expression for energy density. So that is energy emitted by a blackbody in certain wavelength range, say d lambda, lambda plus d lambda. And he just designated it as E lambda d lambda. So that E lambda d lambda is equal to some constant divided by lambda to the power of 5 e to the power of minus e2 by lambda t into d lambda. He was able to derive this equation by assuming that the emission of energy or absorption of energy from a blackbody takes place in a continuous manner. So just by using progressive wave concept, he was able to derive this expression. From this expression, it is very clear that this energy depends only on lambda because all other factors are constant. C1 is constant, C2 is constant, temperature is kept constant. So this is taken at a particular temperature. Even temperature is constant. So therefore, E lambda depends only on lambda. And you can notice that you have E lambda depending on lambda to the power of 5, which is inversely proportional to lambda to the power of 5, and E lambda proportional to e to the power of minus 1 by lambda. So among these two functions, so this dominates because it is an exponential function. So therefore, if you plot a graph of E lambda as a function of lambda, you will see that so it matches the shorter wavelength part of the blackbody radiation spectrum. But it failed to account for this drop in intensity towards the higher wavelength part. Then Rayleigh Jeans, so they tried to explain this blackbody radiation spectrum by assuming that this blackbody emits radiation or absorbs energy in the form of stationary waves, because this is continuous process. Emission and absorption is continuous process. So therefore, incoming wave and outgoing waves form superposition to form stationary waves. They calculated the number of stationary waves, and they also obtained an expression for the energy density of the blackbody. So E lambda d lambda is equal to some constant divided by lambda to the power of 4 d lambda. And this is in fact is called as Rayleigh's formula. E lambda d lambda is inversely proportional to 4th power of wavelength. You can notice that if you plot E lambda as a function of lambda, so you get a graph somewhat like this. This is what is Rayleigh-Jeans curve. But the experimental curve is somewhat like this. So somehow you can match this, but there is a failure of this Rayleigh-Jeans law beyond this ultraviolet region of the electromagnetic spectrum. So this is what is termed as ultraviolet catastrophe. So therefore, you can notice that Wien's law was successful in explaining shorter wavelength part of the blackbody radiation spectrum. Rayleigh-Jeans law, so with certain modifications, you can fit into the higher wavelength part of the blackbody radiation spectrum, but it failed to account for shorter wavelength part. But there was no single equation which could be able to explain the entire blackbody radiation spectrum. So therefore, in order to account for this problem, so Max Planck around 1900, he proposed a revolutionary concept. He assumed that this energy absorption or emission from a blackbody is not a continuous phenomenon, but takes place in discrete packets of energy, and he called these packets of energy as quantum. So that is why the new mechanics is termed as quantum mechanics. So that energy of that quantum of energy packet so is equal to h nu, or it is an integral multiple of h nu. So this h is a constant, so which we call now as Planck's constant. So its value is 6.6 into 10 power minus 34 joule second. So therefore, the energy of each quantum depends on its frequency. Okay. So using this, Max Planck was able to derive another expression for this blackbody radiation spectrum. So that is energy density of the blackbody radiation spectrum. According to him, so this E lambda d lambda is equal to some constant, say 8 pi hc divided by lambda to the power of 5, d lambda divided by e to the power of h nu by kt minus 1. So this is the expression. This is what is known as Planck's distribution law. So this is very important law because for shorter wavelengths, you will see that when lambda is small, so this e to the power of c2 by lambda t will be very high, but it will be very high compared to 1. So therefore, this minus 1 can be neglected. So if you neglect this minus 1 in the denominator, this equation automatically reduces to Wien's law. But already we know that Wien's law explains the shorter wavelength part of the blackbody radiation spectrum. So therefore, you will see that the Planck's law automatically reduces to Wien's law for shorter wavelengths. Whereas at large wavelengths, so that means when lambda is large, so this e to the power of h nu by kt will be very small. So then you can approximate this e to the power of h nu by kt minus 1 as this equation. This equation automatically you will see that this will becomes um, Rayleigh-Jean's law. This is Rayleigh-Jean's law. You know that Rayleigh-Jean's law explains the irrelevant part. So that means this Wien's law and Rayleigh-Jean's law appears to be as two special cases of Planck's law. Or in other words, the Planck's law explains the complete blackbody radiation spectrum. So here in explaining this blackbody radiation spectrum, for the first time, Max Planck assumed that so this light consists of stream of energy packets. So they are called as quanta. Till then, light was believed to exhibit only the wave nature. So the particle nature of light was for the first time proposed by Max Planck. But the first direct evidence, experimental evidence for the particle nature of light came from photoelectric effect. Photoelectric effect is a phenomena in which if you allow light on certain metal, photosensitive metals, you will see that there will be emission of electrons, and these emitted electrons are photoelectrons. And this is the experimental arrangement to study the photoelectric effect. So you have a quartz tube which allows the ultraviolet radiation. So if you have some light falling on this quartz tube, it enters and it is made to incident on a photosensitive plate like sodium, potassium, etc. As soon as the light is incident, so the electrons are emitted, and these emitted electrons can be detected through a galvanometer if you connect a galvanometer in this circuit. But from the experiment, what we observe is this photoelectric phenomena is instantaneous phenomena. That means there will be no time delay between the incidence of light and the emission of electrons. So as soon as the light is incident, electrons are emitted. So the photoelectric emission phenomena is an instantaneous phenomena. This instantaneous concept cannot be explained by using classical laws. So these experimental observations were made by two groups, Hertz, Hallwag and Leonard around 1886. They studied this photoelectric phenomena so by using several experimental setups. They noticed that so this is an instantaneous phenomena. The number of photoelectrons emitted depends on the intensity of radiation, and the energy of this kinetic energy of the emitted electrons depends on the frequency of radiation. And for every photometal there is a threshold, that means below which there is no emission of photoelectric effect or photoelectric effect is not observed. So all these experimentally observed facts could not be explained by using classical laws. Say for example, these are the graphs of those experiments. Suppose if you increase the voltage, then you will see that the current also increases. This is for different intensities of light and then saturates. This saturation concept cannot be explained by using classical laws. Further, on the negative side, so if you increase the voltage in the negative direction, that means just by reversing the polarities if you do, you will see that you are just keeping the potential opposing the electrons reaching the collector. So therefore, for a particular voltage, negative voltage, so the number of electrons reaching the collector becomes 0. So this is independent of intensity of radiation, which cannot be explained by using classical laws. See, for all intensities of light, so you have only one stopping potential. Stopping potential is a measure of kinetic energy of the electrons. So kinetic energy seems to be independent of intensity of light. So this cannot be explained by using classical laws. On the other hand, if you take this graph, you can notice that there is a threshold for metal. Say if you plot stopping potential as a function of frequency of radiation, you get a straight line. But there is a minimum value of frequency below which there is no photoelectron emission. And you get straight lines for all the metals. The slope of all these straight lines will be same. And that is of course Planck's constant which I cite. So this threshold concept cannot be explained by using classical laws, because if you use classical theory, as you decrease frequency, so there should be more time delay. So only time delay should increase. But you never find photoelectric emission at all below this frequency. There is a threshold. This threshold concept cannot be explained by using classical laws. So these are some limitations with the classical wave theory. First thing is photoelectric emission is instantaneous process. So this cannot be explained by using classical laws. And